All right. Well, hello, everyone, and happy Friday. So my name is Ashu Jaiswal, and I'm the program lead for Compute Ecosystem for Developers here at OCI, Oracle Cloud Infrastructure. And we are so glad that you were able to join today to learn more about the capabilities of the OCI A1 platform. Before I introduce our speaker, there's a few house rules to go over. This session will be recorded, which you may have known as you joined this webinar. All the audio lines will remain muted during the webinar, but you can ask questions using the Q&A box, which should appear at the bottom of your Zoom webinar screen. And finally, if you stay until the end of the demo, you can find more information on how to get some special goodies and swag, which are exclusive to this session. Okay, so without any further delay, I would like to introduce our speaker, Victor Jakubik, who's the head of AI at Ampere. Hey, Victor.
Hi, Ashu, and thank you for having me. And pleasure to have all of you with us. Let me share my screen and let's dive right into this.
Sounds good. Please go ahead.
Great. Can you all see it?
Yep, we can.
All right. My name is Victor Jakubiuk, and I'm the head of AI at Ampere Computing. Today, I'm going to tell you how to efficiently run computer vision models on OCI Ampere A1 infrastructure using standard AI frameworks like TensorFlow and PyTorch. Briefly about the agenda. So first and foremost, we are running the demos today. So I'm going to show you a real-time demo processing a video feed from Jackson Hole using a low latency processing on our CPUs. So that's the first demo. And second demo, I'm going to show you a high throughput, aka a batch processing workload, to demonstrate a very effective cost performance of those workloads. Beyond that, I'm going to tell you a little bit more about AI, what AI is, what sort of benefits we can provide as Ampere and as Ampere AI. And I'm going to tell you a little bit more about our software that we call AIO. And lastly, I'm going to show you where to get all of this software for free from the OCI marketplace. So first, what is AI? AI is one of the fastest growing workloads in the cloud and on the edge. Now, AI is a vast term. AI has been with us since at least 1950s and encompasses many different things. What we're focused here in this demo is particularly deep learning, which is a subset of machine learning, which in turn is a subset of AI. What machine learning is could be anything that involves computers processing numbers and data. So with a very simple machine learning could be something like a linear regression in your Microsoft Excel spreadsheet, all the way to your typical voice recognition applications like Siri or similar. The latest and greatest innovation in AI came from deep learning, which started about 2010 with the growth of compute power. So today in this presentation, we're focused on deep learning. Now, specifically in terms of what we as Ampere can provide here, or as Ampere AI, we're focused on AI inference in particular. Ampere AI is a software team within Ampere that helps with all sorts of AI workloads, primarily deep learning, but primarily AI deep learning inference. The team was started last year when I and my team joined Ampere via the acquisition of my company called Onspecta. So what's coming up here? So here we're primarily focused on computer vision demos running standard AI frameworks. So today AI developers primarily use TensorFlow and PyTorch as their AI or computer vision frameworks. So we're going to use those, in particular, we're going to use TensorFlow using all sorts of standard AI tools, using Python, Jupyter notebooks, and such a workload on our AI A1 instance on OCI. And we're going to show you the benefits of low latency, that is a real-time processing demo, and a high throughput, that is a kind of a batch processing demo. You will be able to use all those demos. They're available for free for download from GitHub. And our software is also available for free. So you can try our Ampere optimized TensorFlow and Ampere optimized PyTorch at any time on OCI A1 instances. Very briefly about AIO. AIO, which is our core Ampere AI software, that is AI optimizer. This is the software layer that sits in between frameworks and the underlying hardware. So in particular today, if you're an AI developer, you're most likely using TensorFlow, maybe PyTorch, or similar frameworks like Onyx or TensorFlow Lite. What we do for you here is we help you deploy this framework onto our Ampere Ultra CPUs, and we help you get very good performance out of this. And by very good performance, I mean we can provide you with up to 5x inference speedup over non-optimized TensorFlow and PyTorch frameworks. And we can do this for both latency and throughput workloads. And essentially any type of AI model that you can run in those standard frameworks like TensorFlow and PyTorch, you can run with our software. The software is available for download for free, and it doesn't require you to do any sort of API changes. It doesn't require you to do any sort of model conversion, and it preserves the accuracy of the model. So we're not talking about shaving off accuracy by 10% to get you 2x speed up. Everything stays numerically the same. In other words, AIO works as some sort of a backend to those standard frameworks, kind of like a software shim layer that lets you run those frameworks. And it's different from other alternatives out there that it doesn't require any of this conversion. All sorts of different packages out there require you to convert a model. So for example, if you start with a TensorFlow model, they may require you to convert to an Onyx model, and from Onyx to something else. We don't do that. If you start with a TensorFlow model, you will be running a TensorFlow model using our Ampere optimized TensorFlow. No API changes required. No conversions.
Hey, Victor, so we have a question.
Yes. Yes. What's the question?
By optimized, does it mean it's optimized for the AI hardware?
Yeah. So AIO is the software that optimizes TensorFlow and PyTorch and other frameworks for our Ampere Ultra CPUs. That is, it optimizes for our A1 instance on OCI.
Great, thank you.
And maybe to just one more thing to clarify this, we're not providing here any custom AI acceleration software. We're primarily focused here, hardware, we're primarily focused here on just on software. Okay, so where to get this Ampere optimized TensorFlow and PyTorch? There are a couple different methods. The easiest for most of you would be to go to the Oracle Cloud Marketplace. You can click these two links. There's Ampere optimized TensorFlow and Ampere optimized PyTorch available. They are pre-configured there, so you can start an OCI A1 shape with however many CPUs, and you can get this up and running. Alternatively, you can download this. You can download our software from Ampere Solutions website. That's also available there. And if you need some custom packaging, feel free to reach out to us, and we can discuss that as well. The software is available for free with a very simple license, so you don't have to you don't have to pay for this any extra, and you don't have to sit through complicated licenses. Once you download the software, or once you start the instance, it will immediately come preloaded with a few examples, including Python Jupyter notebooks with a few sample models. So you'll be good to go, and you'll be able to play with those little examples from the very beginning. All right. So that's the overview of our software. Now, let me tell you about the demo that we're going to run here. So the demo is set up as follows. We have a camera out there. It's a publicly available camera streaming from Jackson Hole, Wyoming. The stream is coming from YouTube. We're ingesting that stream in real time. So everything I'm going to show is actual real demo in real time. We have started a OCI A1 instance. And our Ampere A1 shape is running standard AI or deep learning software. So we're having an IPython kernel that is a Jupyter notebook running Python. On top of that, we have our Ampere optimized TensorFlow that is running AIO in the background. And what we're doing there is we're detecting cars on an intersection in Wyoming, in Jackson Hole. And we're marking those cars on the images, and we're doing that in real time. And real time here means we're doing this at 30 frames per second. We're going to run this demo on our Ampere A1 shape using our Ultra CPUs, but we're also going to compare that against an x86 instance running on another cloud vendor, and also on a Graviton server running on AWS. It will be the exact same code running on all three, and I'm going to show you the advantage of using our platform, both in the software and the hardware scenario. So I'm going to briefly switch to the demo here. So I'm going to exit the presentation and pull up the code. So what we have here is, I had already started an OCI A1 shape running 6 OCPUs. And I have started that along with our TensorFlow, Ampere optimized TensorFlow virtual machine. And it's embedded with a Python Jupyter notebook. So it's running in very standard Python software stack. As you can see in this code, we're importing standard libraries. So standard Python libraries like time, sys, OpenCV, NumPy, as well as TensorFlow. And this is sort of the kind of the core of this presentation. We're running standard TensorFlow or Ampere optimized TensorFlow. And as you can see, we're not importing any custom libraries. We're not importing any sort of conversion software. This is standard TensorFlow using standard APIs. After that, here we're initiating a bit of streaming code. In this case, this is the video stream. So this is mostly boilerplate code. So I'm going to skip this, but basically we're just pulling the video from YouTube and processing it frame by frame. We have a little bit of code here to draw boxes and draw the frames per second or the latency on those videos, but that's also fairly basic OpenCV code. Notice again, we're not using any custom libraries. It's all standard Python data science and computer vision libraries. So here's the actual core of the demo. Here's the YouTube link that we're processing the video from. Again, this is Jackson Hole. We're taking the video and processing it frame by frame. Since we're running on 6 OCPUs on our A1 shape, we set the number of threads to 6 to fully utilize them. And we initialize the standard TensorFlow code that's done over here. We import the graph and we import the actual model. The AI model that we're running here is a model called SSD MobileNet v2, which is an object detection model, fairly standard model for computer vision. It consists of two parts. The backbone of the network is MobileNet, and then there's the SSD part, or single shot detector, that actually does the object detection and detects multiple objects. This model has already been pre-trained, so it's already trained on various images from ImageNet and similar. So all we're running here is just inference of this model. We're not training the model, we're running just the inference. What we're detecting here with this model is the actual classes of objects. We're detecting boxes, that is the bounding boxes around them. And we're also bringing in the confidence score of that model for their particular detection. Now, back to the core of this code. We import the video stream over here, and we iterate over every single frame as the video counts. So here you can see the actual code to call into TensorFlow and for a particular frame, and get the results, get the bounding boxes for that particular frame. We measure the time from the beginning of this execution to the end of this execution. And we then draw the boxes along with the performance, along with the latency in milliseconds of running that workload. So it's a fairly typical computer vision workload to process images. And of course, you can see that this is happening in real time, right? We're processing frame after frame, so we're not batching multiple frames together. We can process the next frame only after we had finished the previous frame. So this has to, in order for this video to display nicely on a computer, it has to run in real time. And what real time means is we need to hit about 30 frames per second. 30 frames per second, that's about 31 milliseconds per frame. In other words, this entire call to session.run has to finish execution within 31 milliseconds or less. Otherwise, the video is not going to be processed in real time. So we can run this. We can run this notebook, and we get the results of this video processing here. And just when I run this demo, it's we have to run this again. Oops, sorry about that. It's live demos always. Sorry about this little mishap. I'll bring this back in a second. But rest assured that we can run this demo within 31 milliseconds per frame on this 6 OCI 6 CPU server. Now, to run this, to compare this to maybe another demo that we have available here, we can also we can run the exact same code, for example, on an x86 machine. And I'm going to walk you through this again. So this is the exact same code running video stream from YouTube, the exact same Jackson Hole camera. We can run this video here. Again, the exact same SSD MobileNet v2 model, running everything in real time. And sure enough, we can run this on, in this case, on an AWS M6i instance using 4 vCPUs. You can see that the processing of this is about 31 milliseconds, which is about 30 frames per second. Now, what we have done here is we've picked the minimal number of OCPUs or vCPUs required to run this demo in real time. So on x86, this requires 4 vCPUs. On our Ampere Ultra machines, this requires 6 OCPUs. And if we were to run the exact same demo on the Graviton server, and let me pull this up right here. This requires, and again, the code is exactly the same, running a video stream from YouTube, running the exact same SSD MobileNet model. On the Graviton server, that is M6G on AWS, this requires 48 vCPUs. Let me just give me 1 second, trying to reload the other demo.
Okay, while Victor is bringing up that demo, if you have any questions, please do type them in the Q&A box.
Now here's this demo. Sorry, I had to switch the video stream to another camera. I think we had some little demo failure. Apologies for that. But again, it's the exact same code. Also running SSD MobileNet model, processing this frame by frame. And you can see that with 6 OCPUs, we can hit a latency of 33 milliseconds, which is about 30 frames per second as well. Now, so let me compare this kind of like side by side. So we can run a real-time processing demo with 6 OCPUs on our Ultra machines. To run the exact same demo on an x86 machine, this requires 4 vCPUs. And to run this on Graviton, also in real time, also about 30 frames per second, this requires 48 vCPUs. So what does this mean for you as a developer? Obviously, we're running the exact same code, but the number of OCPUs required is different. So what is the benefit for you as a developer? Well, let me show you. The primary benefit here is cost. It's cost of your workload. And as I'm about to show you, the cost advantage is ginormous. So again, remember, the setup here was what's the minimum number of cores that you have to run on your server in order to be able to process this video in real time. That is about 30 frames per second. We showed you that on our OCI Ampere A1 shape, this requires only 6 OCPUs. The cost of running this workload per hour is $0.084. That is 8.4 cents per hour for running this workload. To run the exact same workload on an AWS M6i instance, this requires 4 vCPUs. And the cost of running that is $0.192 per hour. And if you compare this to the M6G 12x large, that is the Graviton instance, in order to run the exact same video at 30 frames per second, you need to have 48 vCPUs. The cost of running 48 vCPUs there is $1.84 per hour. As you can see, the cost advantage is huge. It's well over 2x when comparing to the M6i instance, and it's well over 10x when compared to the Graviton instance. Note that both all three instances were running the exact same TensorFlow code. So there's no changes in APIs. There's no custom optimizations done to all of that. we're using our optimized TensorFlow on our A1 servers. On Intel, we're using Intel optimized TensorFlow, and on the Graviton servers, we're using just regular TensorFlow, as TensorFlow doesn't have any specific optimizations for Graviton. So all of those packages kind of working out of the box gave you 2x advantage on our OCI Ampere A1 servers. Any questions so far?
Hey, Victor. So one of the questions was, how would this perform with 4 cores, which is part of our AFT?
So with 4 cores, you mean with 4 OCPUs on OCI Ampere A1?
Yep.
Great. So good question. So with 4 OCPUs, you probably wouldn't be able to hit real-time performance without doing some further optimizations. So you would probably be running this at 20 frames per second. So remember, the point of this demo is to get the minimum number of cores on each of those servers to hit real-time processing, that is 30 frames per second. So that's from the performance side point of view. That being said, if you were to scale down the number of cores needed, sure enough, the cost scales linearly, right? So using 4 OCPUs instead of 6 OCPUs, you would have what, 30% cost savings. So the cost would further decrease. So in terms of price performance advantage, it would remain the same. It's just the performance may not be exactly hitting 30 frames per second.
Got it. Thank you.
Great. So that's one demo. But now, not all workloads need to run in real time. Some of you may have workloads that require processing in batches, or maybe you just don't care about the latency of the workload. Maybe it's okay for you to wait a minute or 10 minutes or an hour to get this video done, or maybe you're just running this workload overnight. In which case, oftentimes you can process the video or a set of images in a batch. And you can increase the batch size anywhere from 1, in which case you'd be running in real time, to a couple thousand. So we have another demo here doing the same sort of comparison of OCI Ampere A1 with our TensorFlow, with our Ampere optimized TensorFlow, as well as the AWS M6G and M6I servers. And again, it's the same setup where we're picking the best possible configuration for each of those servers. And in this case, we're picking the number of cores on each of those servers that give you the best performance per dollar spent. So again, let me show you the actual demo. So what we're doing in this demo is, and I'm going to show you the results first, and then I'm going to walk you through this, is we're taking a set of images, in this case, images of dogs, and we're running computer vision on them. Specifically, we're running a segmentation network called UNet to detect where those dogs are in those images and to draw their boundaries. So from this picture, we get something like this. From this picture, we get a line out of a dog over here. Now, the pictures here are minimized a little bit for further processing down the road, but it's the same principle. These sort of workloads are oftentimes used when processing videos in any sort of computer vision, in surveillance, or in automotive. You can imagine that if this is an automotive application, instead of processing dogs, you would be processing, for example, road signs from multiple cameras at the same time. So what we're doing here is, well, first we need to download the data set, and this comes from Oxford University. And we're running a network called UNet, which is, again, a fairly typical network. Notice here, we're importing a bunch of libraries, but again, all of those libraries running on our OCI A1 are standard data science and computer vision libraries like TensorFlow, NumPy, or PIL, which is an image processing library. We initiate TensorFlow, this time using 2 threads. We're running this on a 2.0 CPU shape. And we load the data. This is kind of a boilerplate code to actually load the data. And we initialize this repository called Oxford Pets with 4,000 images. So there are 4,000 images that are being processed in the background. Notice here, the way we're measuring time is for processing of all of those 4,000 images. So we're not processing them one by one. We're processing them. We're processing all 4,000 at once. So this workload may take a little bit of time to run, but because we don't care about the real-time performance, all we care about is like the total cost to run this workload. That's okay. And lastly, here we're displaying a sample of 10 of those images, just as I showed you seconds ago. So if you run this entire workload that is processing 4,000 images, this workload will complete in 181,000 milliseconds, which is 181 seconds. So that's the total time to run this workload. Now, I'm not going to obviously flip through every single one of those images, but you can imagine that those images get processed, and you can go through all 4,000 of those afterwards. Now, if we were to measure the actual performance sort of per second, with this network, we're processing something like 5.5, so 5.5 image per second of the compute. So this number by itself may not mean too much. Is 5.5 a lot? Is it not a lot? It's hard to compare that to anything. But where we can compare this is the actual total running cost of this workload. And again, all these workloads are available in GitHub, so you can go and try them yourself, and you can try them out. So let me show you how this compares to other options. If we were to run this demo on our Ampere A1 server with 2.0 CPUs, the cost of processing, the cost of running the server is $0.032 per hour. In other words, 3.2 cents per hour. Whereas the cost of running an Intel server is $0.096, also with 2 vCPUs. And the cost of running a Graviton server is $0.077 per hour, also with 2 vCPUs, so 7.7 cents. Now, if you look at the raw performance of running those workloads, we have very significant cost advantage. This is normalized cost. So we set this value to 1. And if you compare the exact same time required to run this workload on an x86 machine, we're looking at 2.3x advantage over the M6i large instance. And we're looking at 3.4x advantage over the AWS M6G large instance. And again, the results that we're going to get are exactly the same. The time of running those workloads will differ because each machine will have a different performance. But since this is a throughput or batch processing workload, we probably don't care too much about raw performance. What we care about is raw cost or cost performance. And this is where we get our very significant advantage. Any questions on this so far?
Nope, I think we are good. You can keep going.
Great, thank you. So everything I have shown you so far here uses standard TensorFlow that has been optimized by Ampere on the backend using our Ampere inference optimizer that we call AIO. This works equally well with PyTorch as well as other frameworks. And of course, we're expanding the frameworks available here over time. As I have shown you, we can deliver very high performance for kind of critical workloads or real-time workloads that require a very low latency. And we can do this also very cost effectively. For high throughput workloads, that is for batch processing workloads that don't necessarily require low latency, we can provide a very good cost performance. And as I have shown in the code, all of this is using standard frameworks with no recompilation, no API changes, and otherwise no modifications to your workload. You can take your model that has been trained elsewhere or on GPUs, and you can deploy that on our CPUs at any time. Now, to learn more about our software, you can go to our Ampere AI Solutions website. You can click this link over here. Or you can start the VMs directly on the OCI marketplace. So we have our Ampere optimized TensorFlow available over here on this link. Or you can try our Ampere optimized PyTorch over here. Both VMs come preloaded with those examples, as well as a few others. So you should be able to get going very easily. All right, with this being said, I think this wraps up my presentation, and I would love to open this to questions. You can sign up for 1 year of OCI A1 trial by clicking this link over here. And Ashu, off to you for that quiz.
Yeah, thank you, Victor. That was great. So if you have been following along, please remember to take the PyDay quiz. It has questions from this presentation and others. And if you actually, if you get the questions right, you can win cool prizes. So just to reiterate, if you'd like to sign up for a 1 year trial instead of a 30-day, please follow this link, and you should be able to take advantage of the OCI A1 platform in its entirety. Also, we have some Slack channels specific to PyDay. This is our link to going to the Slack channels. And if you follow those, you should be able to get more information, not just related to this presentation, but to all the other presentations which have been taking place today for PyDay. Again, Victor, thank you very much for your presentation. Everyone else, thank you for joining. There's still a lot of great sessions going on today for PyDay, so please check them out. And we hope to see you in one of those other sessions. Thank you.
Great, thank you, Ashu. Thank you, everyone.
Thank you.